So now we are going to talk about how do we make a guess for g of t. We did it for a polynomial, which was, I think, a fairly obvious guess. But now we are going to expand it to other types of things. There is a table in your book, table 3.5.1, but I'm basically going to summarize it. So let's break it down into g of t and then our guess. So if we have a polynomial, let's say, I don't know, a t to the n, we discussed then that our guess was going to be, oh, I need to use another letter besides a. We're going to go with b, t to the n, so I can use a's over here. Our guess was a to the n, t to the n, plus a to the n minus 1, t to the n minus 1, all the way down to a1t plus a naught. Right, so you're just matching that degree. Let's say we have e to the alpha t. Ideas on that guess?
E to the alpha.
Yeah, e to the alpha t, but we're going to throw some coefficients in front of it, right? So it's just going to be a e to the alpha t. What if we have b sine, well, I'll just do sine. Just write sine alpha t.
Sine alpha t plus cosine alpha t.
Why do you need that cosine in there?
Just the nature of sine and cosine functions.
Yeah, just the nature of sine and cosine, right? Because when we're taking derivatives of sine and cosine, we're flipping back and forth between the two. So even though at the end you ended up with sine, along the way you probably had some sines and cosines in there, so you put both so you can capture all of that. So you would do a sine alpha t plus b sine alpha t. And I didn't write a coefficient in front of e or sine, but if you have just a coefficient in front of those, it actually doesn't change your guess, so you don't need to worry about that. Okay. What about if we have a sum or a product of any of these? Yeah, just add your guesses together, right? So let's say we had, I'll go t squared e to the 3t. Then my guess would be my t guess. So that would be a t squared plus b t plus c times e to the 3t. So your guess is just a sum or a product of your guesses. Yes.
Would we need a coefficient for e to the 3t, or would the coefficients in the polynomial just absorb that?
Right. So if I put a coefficient in front of here, if I had a like d here, I could distribute that d and absorb these into the coefficients, right? So it is not wrong to put it there, but you don't want to have more letters than necessary to solve for, right? So by just saying that's just going to be absorbed in, that's fine. So what you'll find is with those products, it is often absorbed into one or the other of them, but not for these sums. So for the sums, you're going to need the coefficient for both of them. So let's just do a contrasting example of t squared plus e to the 3t. Then we would have to do AT squared plus BT plus C plus D e to the 3t, because you don't have the distributed property to absorb that other constant. That makes sense? Okay.
Can you go back to the sine one?
Yeah.
Why do we have a sine plus b sine?
Because one of these should have been a cosine.
Okay, just checking.
Yeah, great catch. Writing wrong things all over the place. And again, that goes back to that cyclical nature of sine and cosine when you're taking derivatives. Okay. So the last kind of thing I need to make you aware of has to do with exponentials. Okay. So let's say we had our complementary solution of, let's say we had C1 e to the alpha t plus C2 e to the beta t. And then let's say our g of t was e to the alpha t. So we have both of these things together. What do we notice about our complementary and our g of t?
They share a term.
Yeah, they share a term, right? They share this term. So your guess cannot just be e to the alpha t, because you've actually already absorbed, like that guess is already in here. So think back to our repeated roots. What ended up happening when we had a repeated root? So we really had like e to the alpha t and e to the alpha t. Yeah, we put a t in there. We're going to do the same thing here. You could go through the process of like dealing with the Wronskian, but you're always, the same thing is going to happen. So your guess would be a t e to the alpha t. You can extend that even a little bit more. So let's just do one more special case. So let's say we had our complementary solution of C1 e to the alpha t plus C2 t e to the alpha t. And then our g of t was e to the alpha t. So I've already got an alpha t in here, and I've already got a t alpha t in here.
T squared.
Yep. So your particular would be of the form a t squared e to the alpha t. That again comes from the Wronskian, but we've done a lot with the Wronskian, so we're just going to accept that that will work now. All right. Feeling okay about making these guesses?
The last two cases are when the power of E are the same.
Yeah. So in your g of t, your power, your exponent is already encapsulated in your complementary. Yeah. So it's like two separate cases. Does it show up once or does it show up twice?
When your g of t is a trig function, specifically sine in this case,
Mhm.
The alpha and the alpha t portion, that's not something that we're solving for, right? That's,
No, so that would be like if you had sine of 4t.
and you just keep that no matter what.
You just keep that, right? Because when you're thinking about like, if you eventually got down to a sine of 4t, that means your original needed to have a sine or a cosine of 4t in it. Because the only way to get a sine of 4t from derivatives is to already have a 4 in that trig function, right? Because when we take derivatives, that inside stays the same. Other questions? All right, so we've got number 4 on your in-class assignment. These get really algebraically intensive, so you can use whatever method you would like. So Mathematica, asking the internet to get your complementary solution. I'm okay with that. And then once you like set up your system of equations, you can use whatever you would like to solve that system. If you'd like to use Mathematica, Symbolab, I don't care, whatever you would like to use. Okay?